Okay, so just a few overview kind of things when it comes to dealing with the content of this note. So the reason why you've been sent to, I guess, teach yourself this notes is because there's a lot on here that is really just conceptual stuff that should be pretty approachable in terms of teaching yourself. But nonetheless, I do this video to help you guys, well, just to kind of point out a few important things about this, key ideas, and maybe explain a couple little things along the way. So first of all, mole is one of the SI base units. It's one of the things that, as a reminder, it's a measure of quantity. So being that it's a measure of quantity, it tells you the amount of substance. More specifically, mole is a number, and the number mole is this number, just like the number pair refers to the number 2, or a dozen refers to 12, a mole refers to specifically this number. It's just a name that refers to a particular number. And how is it the quantity of substance? That's the number of atoms in 12 grams of pure carbon-12. So 1 mole of anything contains that many particles of something. So a mole of sodium atoms contains that many sodium atoms. A mole of nitrogen atoms contains that many nitrogen atoms. And we tend to kind of simplify it down. Instead of saying a mole of nitrogen atoms, we tend to say a mole of nitrogen. But nonetheless, a mole of nitrogen, we mean to say a mole of nitrogen atoms that contains that many nitrogen atoms, etc. Or for any element. This is really kind of all the same. So it's called Avogadro's number after the guy who discovered it, but that's the thing that's really important, is we need to understand that when we say you have a mole of something, we're saying we have a quantity of substance that contains this many particles. That's what we mean when we say we have a mole of something. So, let's see. The number mole is actually goes on more decimal places than this, so there's quite a bit of digits to it. So we take this giant number and turn to scientific notation. We do it this way with 4 significant figures. So be aware that anytime, anywhere, any calculation done with this number will never end with more than 4 significant figures. So this particular question, it has been asked, why is this infinite sig figs and not 1 significant figure? Because after all, if this was 1 sig fig, then you should have 1 sig fig here. And the answer is, when it's exactly half a mole, when you have half of something, that's like half with infinite sig figures. It's like exactly half. There's like as infinitely half as you can possibly have. So when we say, and that's why it's written out as the word half, this is a kind of hint that it's infinite sig figs. When you write out the word half, it's like exactly half. And I even added this to make it even more clear. That's infinite sig figs for this number, compared to if I wrote 0.5, you would treat that as one significant figure. This is just, the only reason this appears like this is that you got to type something into your calculator. So there you go, this is what you type into your calculator, even though it's infinite sig figs. So that times that, divided by that, and since it's divided by this doesn't change anything, we just say this times this equals this. So I should back up and say conversion factor. 1 mole is equal to that many particles of something. So a mole of atoms is that many atoms. That's where this conversion factor comes from. A mole of atoms is that many atoms. So a mole of donuts, likewise, is that many donuts. So that's where we get this conversion factor from. Now notice, moles cancel moles to give atoms in the answer. Once again, moles cancels moles is going to cancel moles to give just donuts in the answer. And so that's what that looks like. That's why it looks like that for that reason. Essentially, the calculator would be this times this equals this. Notice, now instead of spelling out a word, I have it in numbers, which is a hint that you count the significant figures. 2 sig figs, 4 sig figs, 2 sig figs in your answer. Now, when it comes to this is shorthand. What we're really saying is how many atoms in this many moles of arsenic atoms. So what we do is we say, okay, take this number, you take what you're given, write that down, set up a conversion factor. Because we know that 1 mole of arsenic atoms contains that many atoms of arsenic. So I put 1 mole down here, that way it can cancel with moles here. So moles is going to cancel moles. I'll even grab a pen, and this is something good to do. You put slash to the units that cancel as you do these calculations so that you know what you've canceled and what you're not canceling and what therefore will be remaining in your final answer. So atoms of arsenic remains. So this times this equals that, the final answer. This is 5 sig figs, 4 sig figs. That's why you have 4 sig figs in your final answer. It's because this is not a definition. This is rounded from what the actual real number is. And when you round a number off, it may have been a definition before, but it isn't anymore. So 4 sig figs. And again, as a reminder, no calculation done with this number will ever result in more than 4 significant figures. Now, if we do the same sort of thing the other way around, if I give you atoms, you're going to have to take this sort of thing and rearrange it to make it so that you have atoms cancel atoms to give moles as your final answer. So once again, you write what you're given, set up your conversion factor, because we're going to just convert moles into atoms. Oops, I had that backwards. Atoms into moles. This is my plan, so that's one conversion, one arrow, one conversion. There's the conversion. So I need atoms and moles in here. So I'm going to put atoms on bottom to cancel atoms here, and moles on top, that way I can get an answer at the end with moles. So 1 mole of sodium, it's asking 1 mole of sodium, actually 1 mole of anything contains that many particles of anything. So a mole of sodium atoms is that many sodium atoms. So a mole of sodium is that many sodium atoms. So atoms cancels atoms, giving moles of sodium as the units of your final answer. So this times 1 divided by 6.022 times 10 to the 23rd, or just simply that divided by that, gives that answer. Note 4 sig figs, 3 sig figs, so 3 sig figs in your final answer. Okay, once again, we just had to notice that units must cancel, and we'll keep using this conversion factor. Moles equals this number. A mole of something is this number of something. A mole of sodium is that many sodium atoms. A mole of arsenic is that many arsenic atoms, etc. Now, let's get these out of the way. When it comes to molar mass, what you're going to do is notice that being that a mole of anything is that number, the size of the things makes a difference. After all, think about a dozen. A dozen mice weighs different than a dozen elephants. It's the same number, but it's a very different weight because elephants are much bigger than mice. Likewise, atoms of mercury are way bigger than atoms of sulfur or atoms of iron or iodine. So that means that even though you have the same number of atoms of each of these, the mass of mercury is way greater for 1 mole of mercury than it is for a mass of 1 mole of sulfur. And where do you get this? You get it off the periodic table. So your periodic tables, I'll grab one from over here. These numbers here, generally at the bottom of the periodic table or so, tell you the mass of 1 mole of that substance. So as you can see right here. So the mass in grams of a mole of the substance. So for our purpose, well, I'll mention something about rounding in a little bit. So it comes from the periodic tables where you, the student, is going to find this information. And basically, it's just, again, it's because an iron atom is bigger than a sulfur atom, which means a mole of iron atoms weighs more than a mole of sulfur atoms. All right, so looking at these, how are we going to actually deal with these? Rounding becomes an issue. There is the rounding rules for addition where you have to count decimal places, but we're going to make it easy on you and say, look, don't worry about it. Just round everything to the hundreds place. You can report all your molar masses to the hundreds place and you'll be fine. So, calcium, if you look on here, it's a little different from what's on here, but we're just going to go with, I suppose this would come from a different periodic table. This is why I round to the hundreds place. I just realized that even as I look at it, different periodic tables will sometimes give slightly different numbers. So oftentimes they'll go out to the thousands place here, and one periodic table will say something different from the next one. So we just round to the hundreds. That way they're a lot more comparable. So 40.08. This one gives a slightly different number, but it's pretty close. At any rate, when it comes to this sort of a thing, we're just going to always round your molar masses to the hundredths place. The only exception, hydrogen, because it's so small, rounding to the hundredths place creates a significant error for these things, so we round to the thousandths place. When you add them together, this plus one of these, it's going to make the hundredths place. So you're generally, whenever you add molar masses together, it's going to come out to the hundredths place, the actual rounding of it. So you can practice with any of these. These numbers on the bottom tell you the mass of 1 mole. So like platinum's 195.05. I'm just checking, or 195.08. Seems to be different from periodic table to periodic table, but nonetheless, you'll find an answer down here that you can work with. So, in terms of these periodic tables, or in terms of like what you're going to do with it, you're going to use these periodic tables to figure out what it is that the molar mass of a compound is. So we're not going to deal with just individual atoms. You got to understand that chemistry involves molecules. So in this case, like hydrogen gas, Hofbrinkel, the diatomic elements, it's not just H, it's H2. So if the formula is H2, that means 2 atoms of hydrogen has twice as much weight. So we're going to take 2 times 1.008, makes 2.016 grams per mole for hydrogen for H2 gas. Remember, hydrogen's the only one you can round out to the thousandths place. Everything else you round to the hundredths. So if it's just hydrogen by itself, you round to the thousandths place. So that's what this is. Someone asked, wait, isn't this 1 sig fig? And the answer is, well, it's exactly 2 hydrogens, so don't worry about sig figs for this. It's like exactly 2. In other words, when it comes to molar masses, just stay with the rounding to the thousandths place or the hundredths place. If it contains anything other than hydrogen, you're going to round to the hundredths place. So a great example of that is here. Although hydrogen goes out to the thousandths place for its mass, carbon is rounded to hundredths place. Oxygen's mass is rounded to hundredths place. See, the oxygen goes out to 16.00. Carbon goes out to 12. Where is it? 12.01. So if these only go to the hundredths place, your final answer is only going to the hundredths place. So that's why it looks like that. So you add 6 times the mass of carbon as shown here, plus 12 times the mass of hydrogen as shown here, plus 6 times the mass of oxygen as shown here. So, given that, what we can do then is, let's see, there we go. So, given that, then we can kind of look at examples. So, like, for example, here we got the methane. A CH4 is 1 carbon, 4 hydrogens. So what that means, if I ask you what's the molar mass, you got to take 1 times the mass of carbon plus 4 times the mass of hydrogen, and that's what this is all about here. So where is the... Okay, this is what I was talking about right here. 4 times the mass of hydrogen plus 1 times the mass of carbon. Add it all up. This is the mass of 1 mole of CH4. The point it made before is valid, that's true. 1 mole of CH4 contains 1 mole of carbon and 4 moles of hydrogen, because there's 4 hydrogens for every carbon. So there's 4 times as much hydrogen as there is carbon. So these points are valid points. Look at those and understand those. But I also just want to make sure we understand that because there's 4 hydrogens, you got to times the molar mass of hydrogen by 4 to find the total mass of hydrogen in each mole of CH4 methane. And then, of course, you add this all up to find the total mass of 1 mole of the entire molecule. And that's how it's going to go for any molecule. For water, it's the same thing. Notice, 2 times the hydrogen mass plus 1 times the oxygen mass is the mass of a water molecule, or water, is the molar mass of water. And the molar mass of water means the mass of a mole of water molecules. So 6.02 times 10 to the 23rd water molecules have that mass. And so we say grams per mole because that's the number of grams that each mole weighs, more or less. Okay, methanol, same thing. A mole of methanol has this weight in grams, which is to say 1 mole of methanol molecules weighs that much in grams. Same thing with calcium nitrate. 1 calcium plus, and oh, be careful about this, 2 nitrogens, 6 oxygens, because 3 times 2, there's 2 of everything inside, so 3 times 2, 1, so I'm all tongue-tied here. 2 times nitrogen right here, so that's why it's twice the weight of nitrogen. 3 oxygens, but times 2 is 6, so that's why you have 6 times the weight of oxygen. So you just got to be careful to count everything up. If you do, you'll notice, by the way, we're still rounding all the molar masses. If it contains other than hydrogen, you round no further out than the hundredths place. All right, now even oxygen gas. And by the way, look at this thing. It's tricky. Oxygen gas. Oftentimes we'll just call it oxygen gas. We're not going to tell you that it's O2. You have to know this. Hofbrinkel. It's a diatomic element. So you have to know when you hear oxygen gas, you have to understand that means O2, which means timesing its molar mass by 2. But be aware, this only applies to pure oxygen gas when it's a pure element not bound to anything else. If it is bound to something else like here, then you don't times it by 2. You just you times it by however many there are. 1 oxygen, 1 oxygen. And by the way, notice the trickiness here. 3 plus 1 is 4 hydrogens, so you make sure to note 4 hydrogens for the mass of hydrogen in that molecule. So these various ones all kind of go the same way. Well, I suppose I'll just bring up here. Okay, CO2, that's 1 carbon, 2 oxygens. Bromine, Br2, it's diatomic elements, that's why it's 2 times the mass of bromine. Helium is not diatomic, so it's just 1 helium, and that's the mass rounded to the hundredths place. Iodine is a diatomic element, so that's why you've times it by 2. Or at least you will times it by 2. I see that you don't have it on here. So the original answer is like, the periodic table says 126.4, I guess. So you times it by 2 in order to get this. And then types are hydrocannabinol, 21 times the mass of carbon plus 30 times the mass of hydrogen plus 2 times the mass of oxygen should add up to that. Your work should look something like this. This is what we want to see if we're seeing the practice. Well, practice. I mean, like if you're doing this on the free response portion of a test, this is what your work would want to look like. So this is a summary of the things you should be able to do for the quiz. And it's a summary of basically the big ideas presented here. So take some time, read it through, go back, review, make sure you're on top of it, because this is the stuff you need to ace the quiz over this. All right, there we have it.